For this project, eventually, after months of work together as a team, we have to use the most efficient material and durability, adaptability, deconstruction, and so on. Foundation is a challenge, okay? The site is very, very tight, so we cannot have a large mat. So we have to deal with foundation, then the superstructure has to deal with architectural requirements, and then the facade. To summarize it generally, we try to have about deep foundation with ball pile all the way down to the weathered rock. And the pile is supported by the mat. The mat is supported by the piles. Okay, we have the hand-dug caissons, and on top of that, we have a thick pile about. Now, this is a layout, and we try to use deep diameter, big diameter ball pile in order to spread the load, and it saves a lot of labor by using deep ball piles and large diameter all the way down to rock. In the podium, we are using the regular smaller piles system. So what you see is a very simple outcome of engineering with a lot of analysis get into it with the optimized design. And we study all kinds of behavior of the mat foundation, including the base rotations and so on, and flexibility and the spring constant. All kinds of engineering were built into to make sure we have the most optimum design, not to waste any construction material. Now the building is separated in different zones, and the structural system is mainly a concrete core, composite concrete core, working with outriggers, and also a mecha frame outside formed by the belt truss. And in addition to that, we have a secondary diagonal bracing to enhance the stiffness for earthquake, the stiffness of the building during earthquake as a secondary system. Well, the main thing is architecture and structure to be in harmony. Every step along the way of engineering, we get to work with the architect, as David has pointed out. So the location of each outrigger truss has been carefully studied with numerous options when we come to this final design. We have done a lot of three-dimensional analysis and with beam modeling as well as 3D analysis, which enhances the optimization process with the architect and mechanical engineers. At the end, you can see and do what a simple engineering product and architectural layout it will achieve. And if you look at the lateral system, we have the core. This is the mecha frame form outside, conveniently located at the mechanical levels, and then we have all these diagonal truss. Even the truss configuration has to be worked out in a simplified way to fit the architecture in order to minimize the obstruction of view for this super tower. Now, the concept of using an outrigger and a core is very simple. The core itself is not stiff enough for a 660-meter tall building. Just like when you try to bend a pencil, it's not stiff enough. But if you try to bend a pipe, it's much more stiffer when you try to bend a pipe. So we work out the outrigger system. And with the belt truss. The belt truss is forming the mecha frame outside the building, which forms like a frame for the secondary system. This is the mega brace. Well, people will ask, why you need a mega brace? Because is your core stiff enough? Is your bracing stiff enough? We have to deal with the China code. This is something that we can discuss later. Now, different codes have their own provision, and different location of the project will have their own projection. For this, in order to meet the seismic requirements and the wind load that we have to deal with, we have to introduce this mega frame. Shenzhen is located north of Hong Kong, which is subject to very high wind load. And if we make the core too big, to make it stiffer, it will decrease the efficiency of the floor plate. So we working with the architect and come out with a solution to have this mega frame and this mega bracing. Now, the structural system will be kept as simple as possible. Basically, we have a core. We try to line up the outrigger system so that we utilize the whole width of the building in each direction in a very symmetrical way to receive overturning, the wind load, and seismic load. Now, in addition to that, we have a bell truss at the mechanical level every 14 to 15 story. And this bell truss is about 2 story deep that forms the mega frame in addition to the very lightweight mega frame system. Now you can see, as David said, we try to push out the mega column, which again, we use a lot of concrete to reduce the carbon footprint. And we try to use high-strength steel to save the material. And then with this working together, we have a very efficient structure and low tonnage. But along the way, we went through many obstacles about how to meet the optimum design. So we have to perform a lot of in-depth analysis, working with the experts in order to come up with this design. This is the core with the link beam. And in some places, we have embedded steel plates to enhance the strength of the core. Again, you know, structural optimization is being done in every step of the way. We also have to look at simplicity of construction. So when we do the detailing of the steel and the structure, we have to bear in mind how to make it simple for steel erection and coordinate with mechanical engineers. You can see this may be a lot of typical design principle that every one of you will know how to do it. But when you go through the process, the amount of depth of work is different from each project. So with the core, with the mega bracing, with the outrigger, the mega frame, we have successfully designed this building that works for architecture with the function requirements set by Ping An Insurance Company. Again, we have to deal with earthquake. Shenzhen is 7-degree earthquake, so we have to deal with that also on the dynamic aspect. So seismic design is another important design criteria in China that we have to deal with. And we have to do nonlinear analysis, performance-based design for optimization, that everybody think that, yes, I know how to do it. But this time we are working with the experts in China. We do site-specific analysis. We do a lot of geotechnical testing. We work with the expert on coming up with the most appropriate seismic curves for this project in order to do the correct, most appropriate earthquake design for this project. So we have to emphasize that you cannot apply what you have done on the previous job and then on the other job, except with your experience. So the design criteria can be different on each project. Now again, we went through a lot of work with KPF and David on the geometry of the building, amount of tapering of the building as it goes up. How do we treat the corner? How do we treat the corner of this building? How do we taper it to reduce wind load, and working with the wind tunnel engineer? On the other aspect of the design, we have other contribution design for the sustainable design, such as natural ventilation. We have heat recovery system. We have high performance facade. We have ice storage, and we have occupancy light control. So you can see a whole series of sustainable design engineering have been built into the project. Thank you.